Let's talk a little bit about DALI wiring. If we look historically, in the last 20 years, we have had a controlled ballast come into the market. If we go back beyond 20 years, the only way we could dim fluorescence was filament transformers, powering the ends of the cathodes of our fluorescents, then modifying the current through the reluctance ballast via a typical phase-controlled dimmer. Because this was done at low frequency, or 50 Hz, we used to get a lot of rippling through the tubes and very poor dimming performance. The only acceptable dimming was above 50%. Ballast manufacturers as well as fluorescent manufacturers of the time realised that this was an issue, and with the advent of modern-day electronics, a lot of the early modern-day ballasts were developed. There was a standard that was developed to interface to these ballasts, so they had a fixed 240-volt supply and then a controlled pair of cables running into the ballast, which was 1 to 10-volt DC interface. Importantly, even though it is only 1 to 10-volt DC, it's regarded as mains-rated interface because there is no segregation from the 1 to 10-volt control terminals and the active and neutral termination that's going into the ballast. Therefore, the cabling that is required for this should be inside the mains tray and should always be a mains-rated cable. As this standard was accepted into the marketplace, the major manufacturers such as Philips and Osram adopted this type of technology. Tridonic went out on their own and they developed an interface called DSI, which simply stands for Digital Signal Interface. This is a very common interface and it's one that we call contractor friendly, mainly because DSI, you don't have to worry about polarity. With the 1 to 10 volt DC signal, you have to worry about polarity because it is a DC signal, therefore you need to make sure everything is wired correctly for it to function. With DSI, it's basically an 8-bit level, which gets sent out on a continual basis from the controller out to the ballast. It's Manchester encoded, which means polarity doesn't matter. DALI was brought in Europe about 14 years ago. DALI was all of the ballast manufacturers getting together, joining into a committee, trying to come up with a common control platform to provide a simple, basic control system. To do large-scale lighting control, it is important that a proper lighting control system is implemented with gateway products. This has been the Philips Dynalite approach. In the product range, we see 1 and 3 universe gateway products to enhance the raw functionality that is available with DALI. As you can see by this diagram, it's a twin pair of cables going in and out, which carries the DALI signal. DALI is very similar to DSI, in which it uses Manchester encoding to get the packets out to the field. It's a two-way communication protocol that if the ballasts are polled, they can actually write information back into the gateway, which is very important for reporting of failed lamps and so forth. Also, we now have intelligence stored within the ballasts themselves, so we can write preset information and group information into the ballast so that the ballasts can perform together. One of the other preferred and simple methods of DALI is to use what is called DALI broadcast. DALI broadcast represents exactly what we could do with DSI, but rather than being native to Tridonic, we now have a methodology where we can control ballasts all together very, very simply, but it's not manufacturer specific. We can use Osram, Tridonic or Philips ballasts and a combination thereof. In this particular system we can see it is being used with the gateway application. We have 3 trophers on a DALI system and 3 control panels. This could be representative of 3 individual meeting rooms. DALI Multimaster is a new implementation of DALI that was verified at the end of last year. Within DALI itself, it is an extension to DALI Broadcast. When we start talking about enumerated DALI, we can have up to 64 ballasts on a DALI universe. Each DALI ballast, when it's bought in its raw format, has an electronic serial number in it, commonly referred to as a long address. This is unique. We can scan our network for those long addresses and then assign them short addresses in the range of 0 to 63. From that short address mode, we can then tell those short addresses to go to different levels, but because of the inherent slow baud rate of DALI, if we address all 64 ballasts on the possible DALI network using short address methodology, we get what is called a Mexican wave effect. All of the lights may not behave together, and we will see staggered switching or dimming. The preferred methodology is, once you have identified and set short addresses, is to then set what we call DALI groups. Per DALI universe, or per 64 ballasts, we can have up to 16 groups. And within each ballast we can store up to 16 presets that is stored electronically in non-volatile memory in the ballast. The byproduct of this is that if you do have ballast failure, the intelligence is stored within the ballast, so that means it will have to be reprogrammed back into the replacement ballast. That process, in a lot of applications, requires a technician. One of the big issues that we have seen historically with DALI networks is we had a twin active. So we went around hooking up all of our fluorescents, then we had a Dynalite cable going around picking up all of our field sensors, panels, etc. And then we would have a third-party cable going around picking up all of our emergency luminaires. From a contractor's point of view, this is expensive because there are 3 lots of cable going out to a particular space. There is 3 times as much fit-off. This has been identified as an issue by many contractors over the years. DALI Multimaster is a new extension to the original DALI, where it allows for some new opcodes to effectively create virtual devices within our DALI gateway. And we use our DALI sensors out in the field that look and work like normal native Dynalite devices. The advantage of this is that we can wire sensors, luminaires, control panels, and now DALI emergency luminaires all on the one cabling infrastructure. This makes a lot of cost reduction for the contractor and brings everything onto a common platform. This approach requires specific gateways, and the current offering is the DDBC120 DALI from Philips Dynalite. This device can have up to 10 field devices, being sensors and control panels in addition to the 64 ballasts. That is the maximum. Those 10 field devices are hosted as virtual devices within that gateway. If you need to go above that number, then you keep adding additional DALI multimasters and hook them all together on the normal Dynet bus. Electronic ballast in the Australian marketplace. This is a particularly important topic because of some changes to AS3000 about 4 to 5 years ago. We now have to put RCD breakers on all field lighting circuits in commercial applications. The byproduct of this is that because electronic ballasts that run T5 or T8, but mostly T5, which is high frequency, around the range of 38 kHz, an electronic ballast provides lots of electrical noise. So to make sure this doesn't get back into the mains, a low-pass filter is on the input stage of every electronic ballast. The diagram here shows what that filter looks like. What it really means in electrical terms is that every ballast has a natural leakage between active and earth of around 1 milliamp. Where we have 35 milliamps RCDs installed, that obviously means that we have a limiting factor of how many we can put on per circuit. That is something that has to be taken into consideration at an installation. Also, because we are also doing power switching of the DALI ballast, what you can do is install a simple MCB back in the switchboard that feeds a 20 amp make or break contactor in our controllers, and then run up to 2 or 3 slave RCDs off the output of that to feed out to the different circuits so that we don't overload any one particular RCD with too much active earth current. Here we are looking at typical mains connections of our big box products or wall-mounted products. Any of the wall-mounted products have intelligent subboards in them. They take a high current from the switchboard. The one shown here is a DBC410. It has 4 10 amp sub-circuits with a 40 amp single phase supply feeding it. This diagram here shows how, if need be, where we have critical applications, we could have non-essential supply and then a contactor changeover to essential supply. What we see in most applications where this is used is that you will end up with a number of products on the essential supply that are crucial, and then a whole range of other products on the non-essential supply side. Every one of these is an intelligent subboard with breakers as part of their sub-circuits. In the Australian marketplace, these products are supplied with RCBs as part of their sub-circuits. The local supply regulations must be observed when wiring all of the mains to control cables. Important to note that Dynet is SELV. Obviously, all of the mains terminations are standard mains terminations. Mains voltages must never be applied to any of the signal cables. Make sure that if you are doing any form of connection, always isolate any of the products. We have seen many instances of where live hookups have been done and mistakes have been made. In a recent case, we had active dropped out onto the shield cable onto the Dynet, which damaged $15,000 worth of product because the contractor did not go into the other room and turn off the supply. Always remember to isolate supply. Also importantly, on the ballast side, if you are using 1 to 10 volt, DSI or DALI, they must be considered mains cabling, therefore they should be in the mains tray. They should be wired in 1.5 mil TPS in a commercial application.